Hey everybody. Tonight we're going to keep building up our knowledge of linear equations and graphing them. So we're going to start with two rough coordinate planes here. Okay, nothing too fancy. And we're not going to mark these because these are just going to be sort of rough approximations of what our linear equations look like. Remember, a linear equation, linear has the word line right in it. Linear equations are always in the form of straight lines. So let's say we have a linear equation that looks like this, and we have a linear equation that slants downward, okay? Both of these are straight lines. Ooh, let me add my little arrow there. I want to look at the domain and range of these functions. Now, in our example on the left over here, we notice that our x values, our input values, right? We have inputs at 0, we have inputs 1, 2, 3, 4, continue to increase, and because it's a solid line, it includes all of the inputs between those integer numbers, right? 1, 1.1, 1.5, 1.9. And that is going to continue to the right on our graph. This arrow shows that it's going to go forever. So we're going to continue in the positive direction. And we're also going to continue in the negative direction because we have -1, -2, -3, continuing to the left, including all those numbers in between because of this solid line. So the domain of this function on the left is all real numbers, because any x value can be used to find a y value. Every x coordinate has a y coordinate. The same case over here on the right, right? This continues to the left forever, and it continues to the right forever. So all x values are part of the domain. If we look at the range of this example on the left, it's the same kind of thing. This graph is going to continue going up forever. So every single y value is represented on this graph. Same thing going down, because this arrow continues down forever. So the range is also all real numbers. Remember, those curly brackets represent a set. So the set of the range, the numbers that are in the range, are all real numbers. And that goes for both of these graphs. Now, there are going to be times when the domain and the range might be restricted. Maybe we can't use all of the numbers. In our first example, the distance d in miles that a runner travels is given by the function d equals 6t, where t is the time in hours spent running. The runner plans to go for a 1.5-hour run. Graph the function and identify its domain and range. So I'm going to underline what the problem is asking us to do. And I'm going to circle or box the important information. We know d represents miles. We need the function d equals 6t, and t is the time in hours. Ooh, and we have a 1.5-hour run. So that's the information we need. So I want to graph this function. If I look at this function, d equals 6 times t. The way this function is constructed, because we have d over here all by itself, it makes the most sense to think of this d as the output, right? Which makes a lot of sense because the distance that the runner runs should be the output, and the input should be how much time the runner spends running. The amount of time will determine the distance. So we will think of t as the input. Right? So if I want to graph this function, I need to create a table. I can have t as my input and d as my output. The amount of time will tell us how much distance the runner covered. Now, I know the runner plans to go for a 1.5-hour run, so we can use 1.5. Right? 1.5 hours, 1.5 times 6 is going to give me 9. We know 1.5 hours will give us 9 miles. Now, if I tried a bigger number like 2, I could put 2 in there. 2 times 6 would give me 12, but that really wouldn't make sense in the situation because the runner is only going to go for 1.5 hours. He's not going to run any longer than that. But he will run for less time than that, right? He will still be running after 1 hour has passed, so we could try 1. 1 times 6 is 6, so after 1 hour he will have run 6 miles. And let's throw another number in there. Let's say 0. 0 is always a good number. 6 times 0 is 0, and that makes sense because after 0 hours, when he's just starting, he will have run 0 miles. So now we can graph this on a coordinate plane. So we'll draw a coordinate plane over here. I'll look at my numbers. I got 0, 0, 1, 6, 1.59. I don't have to go too far on my x-axis. I am going to actually count over here by 0.5s, 0.5, 1, and 1.5. Make sure I'm always counting up by the same amount and I'm keeping my spaces even. And this is going to help me see my graph a little bit better. Vertically, I could mark 1 through 9. I'm going to start with 3s and go 3, 6, and 9. Now I can graph my points. I have 1.59, 1.5 right, and we go 9 up. There's 1.59, 1, 6, and 0, 0. Now, it doesn't really make sense in this situation to use negative input values. When he starts running, he's at 0 hours, right? But it's not like he can run back in time into the negative x values. And it's not like he can run a negative distance either. So all of the times that he can possibly run are between 0 hours and 1.5 hours. And the line that is going to represent this is right here. Now, in this case, we're not actually going to draw arrows. This is called a line segment. That doesn't continue forever in both directions. It has a beginning and an end, right? He begins at 0 hours. He ends at 1.5 hours. If we want to describe our domain and range now, the possible values of inputs for the domain are between 0 and 1.5, right? So we can say that 0 is less than or equal to x, which is less than or equal to 1.5. All of the x values are between 0 and 1.5. For the range, for the distance he ran, all of his y values, all of his output values are between 0 and 9. During this run, he covers all of the distances between 0 miles and 9 miles. So there are our domain and range. Now, instead of giving a time like 1.5 hours like we did in the previous example, let's suppose that that runner instead plans to run a total of 12 miles. Here we're going to do the same thing where we graph the function and then we identify the domain and range. Now, the function hasn't changed. D equals 6t. And the numbers we calculated earlier are going to be the same. We haven't gone over 12 miles yet. But our conditions have changed. Instead of just running 1.5 hours, he's going to run 12 miles. So we know 12 is the distance here, right? 12 is the distance. So if I put 12 in for D, what would T be? I could divide by 6, and I would get T equals 2. So for 12 miles, the time would be 2 hours. So now that we know that value, and we know that that's going to be the maximum value that he ran, we can use that to graph our function. Now, if you look back at our previous graph, right, we only used 1/4 of the graph. We really only used the first quadrant, and we had a point at the origin. So for this one, let's just draw our graph in the first quadrant. Okay, do the same thing. Let's count by 0.5s again, because I thought that worked pretty well. So we got 0.5, 1, 1.5, and 2. And then going up, we can have 3, 6, 9, 12. Now, the points that we had earlier are still going to be there. We still have 0, 0. We still have 1, 6. And we have 1.5, 9. And then now, though, we have 2, 12 also. So once again, this is a linear equation, and we have a straight line, except this isn't a line, this is, remember, a segment, because it has a beginning and an end. Now, we can find the domain. Remember, the domain is all possible input values. Now, in the problem, they didn't tell us what our maximum possible input value was. We know we still have 0, right? You can't run for less than 0 hours. Is less than or equal to x, which is less than or equal to. And now, the maximum input value is 2, because if you're only going to run 12 miles, you're going to stop at 2 hours. So 2. And our range now contains the values between 0 and 12. You can't run for less than 0 miles, and this person isn't going to run for any more than 12 miles. So all of the y values are between 0 and 12. All right, that's it for tonight. I know that was a lot of information, but it's extremely valuable, and it's going to be super important moving forward, so I'm glad we got through it. Have a good night. I will see you all tomorrow.